All right, welcome to our derivative shortcuts lesson. So we're going to use the definition of the derivative here to prove a few things, and get my screen shade up. So first of all, we're going to use the definition of the derivative f prime of x equaling this limit, okay, to find the derivative of f of x equaling 10. Okay, so we're going to find the function where f of x equals 10. Now remember, that's just a smooth flat line. So the derivative, the slope of a horizontal line is 0. It's a horizontal line, so the slope everywhere is 0. So it shouldn't be that hard. Let's make sure it works out. This is what we're looking at. Okay, using this definition above, the limit of f prime of x equals the limit as h goes to 0 of f, where I plug in x minus 10. Well, there's no x here, so there's nothing to plug in. Okay, so it's just 10, minus f of x. Well, again, f of x is 10. So the numerator here is 10 minus 10. We're all over h. Well, that's the same as the limit of 0 as h goes to 0, because 0 over h is 0. So that's equal to 0. So the derivative of a constant function is 0. All right, that was beautiful. That was so fun. Okay, theorem, constant rule. If f is a constant function, 10 or 8 or negative pi, then the derivative of that function is 0. Nothing much to say there. Okay, that's how we write it. And this is the Leibniz notation rather than the Lagrange notation. Last time I think I said it was Newton's notation. I stand corrected. The prime notation is Lagrange. And I'm sure I'm butchering that name. I apologize. I don't speak much besides English. A little Spanish, but that's it. Okay, back to work. So the derivative of a constant function with respect to the variable x is 0. Okay? Pretty straightforward. All right. Example. Find the derivative of the constant function where f of x equals negative 3. What do you think it is? 0. Okay, there's nothing much to say there. Okay, you just turn it into 0. So if you see a constant function, we're going to turn it right into 0. That'll be the derivative. Okay, here's the rule that you are going to love and that you're gonna dream about. If f of x equals x to the n for any positive integer n, then the derivative is n times x to the n minus 1. Okay. There it is. Same statement. Okay. The derivative of the function x to the n with respect to the variable x is n times x to the n minus 1. Here's some examples. Okay, let's start with the first one. I think I can get this to scroll the other way. Okay. Okay. The derivative of x squared is going to be 2 times x to the 2 minus 1, which is 1. Pretty straightforward. Okay. The derivative of x to the 13th. Okay. N is equal to 13 here. There it is. N is equal to 13. Highlight both of them. 13 n. Okay. Now the 13 goes in front, and we reduce the power by 1. Boom. 13x to the 12th is the derivative. So if I want to find the slope of this function at any value for x, I simply plug in x to this equation. All right? Pretty interesting stuff. Pretty neat, really. Now we're going to prove it. I like this proof. You don't have to memorize this proof, but I think it really helps to believe that it's true. Why is this proof true? Well, here's the proof. Okay. Oh, I need to pull this triangle down a little bit. Okay. So here's what we're trying to prove. We're trying to prove that x to the n ends up being n times x to the n minus 1. And here's what it looks like, right? We plug in x plus h in for the variable, boom, minus the function by itself, all divided by h. Now, I've put up Pascal's triangle up here. And this is an application of Pascal's triangle where it lets you basically FOIL out binomials, right? So a plus b to the 0 is equal to 1. A plus b to the 1 is equal to a plus b. That's pretty easy. Now, a plus b squared is 1 plus 2ab plus b squared, right? Pascal's triangle says if you add the two previous above, 1 times a plus 1 times b, you get 2 times ab, right? And again, 1, 1, 3, right? Because I get 1 plus 2 is 3. This is Pascal's triangle written as a binomial expansion theorem, basically. It's pretty interesting. So if I want to take a plus b squared, I go a squared plus 2ab plus b squared. If I want to take a plus b to the cubed, I go a cubed plus 3a squared b plus 3ab squared plus b cubed, and so on. And you can read this down much, much further. I've only written it out to a plus b to the 5th. There it is. Okay? But this is a way we can figure this out. So here's what we get when we FOIL out x plus h just to some arbitrary number. Okay, notice what happens here. If I FOIL this out where n is just some big number or small number, this is what I get. The first one, notice the first is always the first thing raised to that power. So if I'm a plus b to the 5th power, the first term is always a to the 5th power. Okay. Notice also, okay, that the last term is always b to that power. Okay? So I'm not using a and b, I'm using x and h. So the first term here is x to the n. The last term when I FOIL is h to the n. All right. Now we have to look at a couple more instances. Now let's look at the second one. The second one is always, see here, this is going to be a number. Okay. Well, actually, look at this. This is 2. If a plus b squared, the second number is always 2. A plus b cubed, the second number is always 3. A plus b to the 4th, the second number is always 4. A plus b is always 5. Okay, so that's interesting. So this first number here, when I FOIL out, is always n. Okay, good. The second thing that we see here, it's going to be times, in this case, it was a plus b squared, a, b. A plus b cubed, a squared, b. A plus b to the 4th, a cubed, b. So what it is it's always going to be the first one raised to this number minus 1 times this number. It's going to be the first one raised to this number minus 1 times this number. So I'm just replicating that basic thing right here. Okay, it's n times x to the n minus 1 times h. The first number raised to the power minus 1 times the second number. All right. Now, this term here is a way to arbitrarily write the next term. Now, it's not going to really matter in a second. You'll see what I mean. But the next term is some number times x to the n minus 2. So here we had 5. So this one is going to be 4, 3 for the third term, right? First term, second term, third term. We go down powers, right? So n minus 2. And h is going up. Okay, squared, 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 squared. Okay. And then it keeps on going until finally the last term is the second number in your binomial raised to this number. Okay, all right. So we have our expansion. Okay, trust me, that's all I'm asking here. Okay, we look at this and we see the pattern. So there's a little bit of trust here. All right, now let's look and see what happens. Okay, all I did from here to here is I noticed that my first term was x to the n because that's what I got when I FOILed, and I had an x to the n out here. Those two are gone. Okay, all I'm left with now is this second term, this third term, and this last binomial term. All right, but notice one thing that we have in common. Every single one of these terms has an h in it. So we're going to factor an h out. All we did here was factor that h out. Okay, now we are allowed to cancel because I have an h here and an h here, and h is never 0. Okay, because it's approaching 0. This is what we're left with. What kind of function is this? It's a polynomial. Are polynomials continuous? Yes. Okay. So I'm allowed to plug in h equals 0 into this. Sweet. Let's see what happens. The first term has no h in it. It's just what it is. The second term, no matter what this number is, no matter what these things are, no matter what this is, has an h in it. The second term will always have an h in it. So I plug 0 in for h, and this is gone. Boom, boom. The next term will have an h in it. The next term will have an h in it. Boom, 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 all the way down. See? I plug a 0 in because there was an h here. This is gone. The next term will have an h in it. Plug a 0 in, gone. 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 Everything except that first term is gone. And that first term is n times x to the n minus 1. Done. That's our proof. Okay? It's a pretty cool proof, really, I think. Okay, you don't think it's cool, but I think it's interesting at the very least. Okay? If you think it's cool, then right on. Okay, so we're gonna kind of expand these theorems. Okay, so C is a constant, and F prime and G prime exist. Then we're gonna get some formulas that help us combine things. What this says is that if I have a number times a function, I can take the derivative of the function and then multiply the number back in. Okay, that's theorem number one. Theorem number two. If I have two functions that are really, or if I have one function that's really two functions added together, I can take the derivative of the individual functions. Pretty nice, and add those derivatives together. If I have the difference, I can do the same thing. Okay. Notice I do not have a rule yet about multiplication or division. That'll come later, and it's a little bit different. All right. Bennett interrupted me there. Bennett. Anyway, so we have rules that say that if I have a constant, okay, a number times a function is the same as a number. When I take the derivative, I can just ignore the number for a second, take the derivative, and multiply the number back in. That's fine. If I have two functions, or one function rather, that's made up of the sum of two functions, I can take individual derivatives. If I have the difference of two functions, I can take the difference of the derivatives. Okay, so that works. And again, I can't emphasize enough, we can't do this with multiplication, we can't do it with division. Okay, so this is one where those rules start getting screwy. All right, let's do an example here and show you how these things apply. Taking derivatives of polynomials is really easy. Here's how it works. Okay, we have a constant, or rather a coefficient, and we have something we know how to take a derivative of, minus a coefficient times something we know how to take a derivative of, minus something we know how to take a derivative of, plus something we know how to take a derivative of. All right, let's see how this is going to work. The first thing, one of our rules says that if I have a coefficient times a function I know how to take the derivative of, just take the derivative of that function and then multiply that constant back in, or that coefficient back in. Okay? I also know that subtraction, if I have two functions and I know how to take the derivative of those two functions and they're separated by subtraction, that's okay. I can just take the derivative of the first function and subtract the derivative of the second function. So the second function, let's concentrate on this, is a number times a function I can take a derivative of by the power rule. Okay, it's going to be a number. The derivative will be a number, that same number out front, times this second, the derivative of x squared, which I pull the number down in front, and I take x to the 2 minus 1, which is 1. Now, this is one that maybe requires a little bit of explanation. Okay, but subtracting again, okay, we can subtract derivatives from each other. If I have x to the 1 power, x to the first power, and I'm going to freehand this again, so pardon me, x to the first power, okay, I pull down, again, this is the power rule, still, believe it or not. I pull the 1 down in front, okay, and I have x, 1 minus 1 is 0, but anything to the 0 power is 1. So this is kind of gone. This goes to 1. So the derivative is going to be 1 times 1, which is 1. Okay? So the derivative of any x to the first power is 1 every single time. Nice to know. Okay? So the derivative of x is 1, and the derivative of 10 is 0. So I'll just finish it up. That means that the derivative of 3x to the fifth is 15x to the fourth minus 4x minus 1 plus nothing. That's it. Okay. I want you guys, as part of your notes here, to take the derivatives of these two functions. They're not terribly hard, okay? Again, go back and look at the template from the previous one, okay? Every time we see x with an exponent on it, we pull that exponent down in front, okay? We multiply it by anything that's there, and then we take x to 1 minus that power, okay? So x to the sixth will be something times x to the fifth, okay? Anytime we have a constant, it just goes away. Anytime we have something with x to the first, the x becomes a 1. That's it. All right, so I want you to practice these two. We'll look at those in class next time. And then, so pause that once you, and work on those. And then once you're done, I want you just to unpause it, and let's take a look at this next one. Okay, here we go. The next one is 4 to the x, and I'm going to leave it at this today. I know there are quite a few more slides, but we don't need to go any further today. What I want to talk about here is that your power rule does not work here. Your power rule says if your variable is x and we raise it to the fourth, that derivative will be 4x cubed. Your power rule does not apply to this situation. Right now, in terms of a shortcut, we have no shortcut to take the derivative of 4 to the x. Okay? So don't get overzealous. Your power rule works for things like polynomials. Okay? It can also work for some other functions too, but for right now it works pretty much for polynomial functions, which is a huge class of functions and a very useful class of functions. But let's just be very, very clear and very careful that your power rule only applies to certain situations.
Monet Greer, if you're in the building, report to the main office.
Well,
and Mr. Ware, report to the main office. Thank you.
I'm obviously here still at school, so what a better way to end than with an announcement on the PA system. All right, I'll see you guys all next time, and we'll talk about these two problems and make sure that we're all getting the same answers for those. Nice work, everybody. See you next time.